Hello, welcome back. Okay, chapter 9 and half of 25. So the first half of chapter 25 is a type of chemical reaction called redox, so we'll throw that in there. What is a chemical reaction? Good question. That is an awesome picture of a chemical reaction. But if that ever happened in my lab, I would just run out the door. That's crazy. Anyway, so what is a chemical reaction? Chemical reaction is when you take two materials and bring them together and get what's called a chemical change. So it can be pretty simple. It can be such as taking two different particles and smacking them together to make a new one, or taking a particle and then breaking it apart so you break it up into its components, or you can get them to switch parts. But what they all share in common is you'll know there's a chemical change by noticing one or more of the four signs of a chemical reaction. So one of the signs of a chemical reaction is that heat is either released or absorbed in the chemical reaction. If heat is absorbed, by the reaction, that means the surroundings get colder. So when you touch your beaker, if there's an endothermic reaction going on, the reaction absorbs the heat and it gets it from the beaker, and the beaker gets colder. So we would call this an endothermic reaction. And if heat is evolved, that means the reaction is giving off heat, the beaker gets hotter, and we would call this an exothermic reaction. So heat is exchanged. There is a heat change, and that heat exchange we call delta H, which is something called enthalpy. We'll get to enthalpy later. All right, color change. Got to be careful with this color change, because the truth of the matter is it has to be an unexpected color change. For instance, if you paint a car red, although the red paint is electromagnetically attracted to the body of the car, because the paint has positive protons in it, and the metal of the car body or the fiberglass has negative electrons, so they do attract each other, but it's a weak attraction. So if you paint a car red, it's not a chemical change. You haven't created a new material. I mean, that's what any of the chemical reactions, they don't put it down as a sign of a reaction, but you have to create a new material. So you paint a car red, you haven't created rhodium chloride. It's just that you put the red paint onto the surface of the car body. A precipitate is a solid. Pour two liquids together and a solid comes out of it. And bubbles is a childish way of saying gas evolved. So that's why I used it. Gas evolved. All right, so four signs of a chemical reaction. Let's go to your notes on the chapter. All right, so the chapter goes over these four steps of a chemical reaction. Now, do understand, some of these steps can happen in concert with each other. In other words, there are some reactions where bond breaking and bond forming occurs in unison. There are some reactions where a material has to change shape before there can be any successful collisions that result in a reaction. In other words, these four things don't necessarily happen in order, but all chemical reactions have these four aspects to them. First of all, we got to get the reactants to come together. That's what they mean by collide. And bonds between atoms have to be broken. Okay, now that's an endothermic process. You have to add energy to make it happen. So there's always an endothermic phase in a chemical reaction. Step 3, the atoms have to rearrange. Like I said, in some reactions, though, the atoms rearrange first before bond breaking occurs. And then 4, we're going to create new bonds, which means we're going to move a positive proton from atom A closer to the negative electron for atom B. And we said anytime positives and negatives get near each other, it releases heat, which is exothermic. So all chemical reactions have an endothermic part to it, and that is the bond breaking phase. And all chemical reactions have an exothermic part to the process. So the four steps, know the four steps, Know which steps are endothermic. Bond breaking is endothermic, always. And bond forming is exothermic, always. Two aspects to a chemical reaction. There are the materials you start with, called reactants, and the things you create, called products. And the format for writing a chemical equation is to put the reactants on the left, and you put an arrow, which means yield, and then you put your products on the right. So reactants, yield, products. Now an equation is, I like to say a recipe, but it's not. What it is it describes what you have in the beginning, and it describes what you have in the end, but it doesn't tell you how we get there. The pathway by which we get there is something called a reaction mechanism, and we're going to talk about that in the fourth quarter of this course. So for now, we're just concerned with the beginning and the end, and we don't care how we get there. Chemical equations don't just tell you which chemicals are involved and how many. They also can tell you something about the environment in which they're run. It could tell you about the phase in which they're in. So you should know these abbreviations. Little g stands for gas, L for liquid, S for solid. Now, your book uses CR for crystalline solid, but at this point, although we're going to talk a little bit about it in marking period 3, we don't really care about whether they are ionic crystal lattices, metal crystals, or covalent network solids. We're just going to use S for solid instead of CR for crystalline. And then aqueous, the environment. We're going to dissolve this thing in water, so we're going to run it in a water environment. They will use AQ to indicate that. And we can also indicate other circumstances of the reaction. So let me give you some examples. All right. Suppose, for instance, we had nitrogen gas plus 3 moles of hydrogen gas yields 2 moles of ammonia. And suppose this thing has to be run with excess heat. So we can write delta H for add heat, or we can write the temperature at which we need to run this reaction above the arrow, 500 degrees C. So what do we know about this? We know nitrogen and hydrogen are our reactants. Now, there are 2 types of nitrogen. There's the atom nitrogen, and then there's the molecule. Remember, nitrogen is a diatomic molecule. They will just say nitrogen. If they just say nitrogen in the equation, it means the molecule. So we say nitrogen plus 3 hydrogens yield 2 ammonia. So our reactants are the molecule nitrogen and the molecule hydrogen. How many are involved? Well, it goes by moles. Remember we said formulas were mole ratios? Well, chemical equations are mole ratios also. So in this reaction, we need 1 mole of nitrogen for every 3 moles of hydrogen that we react. And ultimately, as a product, that's going to produce 2 moles of ammonia. Now you say, wait a minute, law of conservation of mass, Burnett, 1 mole plus 3 moles, that's 4 moles. How can 4 moles produce 2 moles? How could that be the law of conservation of mass? Well, moles are not mass. And if we take the mass of nitrogen and look it up on the periodic table, it's approximately 14 per atom, so 28 grams. And hydrogen is approximately 1 gram per mole, so that's going to be 2 grams per molecule times 3, 6. So we wind up with 34 grams of reactants. Ammonia, if you add the nitrogen to 3 hydrogens, you're going to get 2 times 17, so you're going to get 34 grams of product. So it is law of conservation of mass. It's just not the law of conservation of moles. But the atoms stay the same on both sides. We have 2 atoms of nitrogen, 6 atoms of hydrogen on the left side, and if you look at the formula of ammonia, we get 2 atoms of nitrogen and 6 atoms of hydrogen. So we didn't change the number of atoms or the types of atoms, so we didn't change the mass. What we changed was the way that they were connected to each other. other things that you can put besides reactants, products, and the phases is above the arrow you can indicate circumstances of the environment. If we put H+, that means let's run this reaction in an acid. If we put OH- above the arrow, that means let's run it in a base. We could put a catalyst, which is something that speeds up the reaction. In this case, it's a piece of platinum metal. We'll talk about catalysts when we talk about kinetics in marking period 4. And let's say we want to hit this with UV light. So we put UV over it. So there's a lot of things that we could put over the arrow to indicate the environment in which we have to run the reaction. So let's go back to our slides. Okay, word problems. Determine the reactants and products, assemble the parts of the equation, and then balance the equation. All right, so I'm going to do balancing the equation in the next video, but for this one, let's work out this one problem. It says, let's write a reaction where aqueous sodium nitrate and aluminum oxide react to produce sodium oxide and aluminum nitrate. Okay, we can do that. All right, here we go. All right, so whenever you have these word problems, step 1, determine reactants and products. From there, what you're going to do is you're going to turn your chemical names into chemical formulas. And this is what we did in chapter 7. So if you had trouble with that, you got to go back and learn it, or else you won't be able to do this chapter either. And then third, once you have all the chemical formulas, then we go back and we put in the mole ratios. And putting in the mole ratios is something we call balancing the equation, which I'm going to dedicate the next video to. All right, so this one. What are our reactants? Well, they made this pretty simple. They used the word react. So we know that sodium nitrate is going to react with aluminum oxide, and I'm going to write that as a word equation. Sodium, I like to put the positive thing on top, nitrate, negative thing on the bottom, and I'm going to react that with aluminum, put the positive thing on top, put the negative thing on the bottom, arrow, which means yields, products, and then again, they were very nice to us. They used the word produces sodium oxide, aluminum nitrate. So I'm going to write that again as a chemical name, sodium oxide plus aluminum nitrate. All right, next step. I got to change these names into chemical formulas, which means I got to go back and use my oxidation states. So what is sodium? Look up sodium, group 1 metal, give it a positive 1 charge. Nitrate is one of those special groups, so it's going to be NO3 with negative charge. So when I put that together, the formula is going to be NaNO3. For aluminum oxide, let's do that in a different color. We look up aluminum, group 13 gives it a positive 3 charge. Oxygen, group 16, negative 2 charge. So let's do our little crisscross technique, which I hate. So we got sodium nitrate plus aluminum oxide yields sodium oxide. Well, we already looked up the sodium, we already looked up the oxide, so I'm going to need 2 sodiums to balance that oxide. And then finally, what color can I use? That color. We already looked up aluminum, we already looked up nitrate. So I'm going to need 3 nitrate groups to balance that aluminum. All right, so there is our unbalanced equation. So step 1, we wrote the words. Step 2, translated them into formulas. All right, now step 3, we got to go back and balance. How do you do that? Well, here's the technique. Guess, check your guess, keep guessing. Balancing is what we call balancing by inspection. There are other techniques as well that are more difficult for more complex reactions. But for now, balancing by inspection is a perfectly legitimate technique. So pick an atom. I have here's my technique here. I have 2 aluminums on the left side, so I need 2 aluminums on the right side. Now I can't change the formula for aluminum nitrate. That's a no-no, because then it wouldn't be aluminum nitrate anymore. But I can put a 2 in front of the aluminum. So now I have 2 atoms of aluminum on each side. I have 2 moles of aluminum nitrate. So that gives me 3 nitrates times 2, a total of 6 nitrates. So I can put a 6 out in front of the sodium nitrate. Now I need 6 sodiums, so I'm going to put a 3 out in front of sodium oxide. And that is my mole ratio. 6 moles of sodium nitrate plus aluminum oxide plus 3 moles of sodium oxide plus 2 moles of aluminum nitrate. I'm going to give you some tips on how to kind of manage that. If you're having trouble seeing how I did it, do not fear. We have the whole video coming up on it. And there was one other thing I wanted to tell you, but I forget, so it probably wasn't all that important. In order to balance these things, though, if you don't write the correct chemical formulas, you never get to the balancing part. It's never going to work out. The aqueous thing. Look, even at the AP level, unless they tell you what phase things are in, we don't expect you to be able to predict it. If they tell you what the phase is, I mean, technically you should write it. So they told us this was aqueous, and they told us this was aqueous, the first 2 reactants, but they didn't tell us what the products were. So even at the college level, they don't expect you to be able to predict the phase until you have a lot of experience with this. So do not worry about it. All right, so that tells us what a chemical reaction is, and what different aspects we can do and put in a chemical equation, and what the 4 signs of a reaction are. So